Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's story will take us into something both familiar and utterly mysterious: light. But not light as simple brightness or the comfort of the day. Instead, we'll wander into a gentler, deeper question. What if every ray of light is a witness? What if it carries with it a memory, not written in words, but woven into colour, warmth, and time itself? Before we begin, take a moment to settle in. Maybe dim the lights around you, or let the hum of the night fill the room. You can close your eyes if you wish. You won't need to see, because tonight we're listening to light in another way. Breathe slowly, like the rise and fall of a wave. There's no need to focus too hard. If your mind drifts, let it drift. We'll still be here, gently unfolding the story of a light, the universe's oldest storyteller. Somewhere, far beyond the clouds and stars, photons, those tiny, tireless travellers, are still crossing the dark, carrying tales from the beginning of time. They are the only true messengers that never stop moving, never sleep, never rest. And yet, within each of them lies a memory, a subtle echo of where they've been and what they've seen. So, tonight, we'll follow them. From their birth in the heart of stars to their endless journey through the void, through dust, gravity, and time itself. And by the end, you may begin to see that light doesn't just reveal the world, it remembers it. Now, when you're ready, let's begin. Imagine standing by the ocean at dawn. The water glows softly and every ripple catches the sunlight for just a moment, then releases it back to the air. That glow, that gentle shimmer on your skin, began its journey perhaps millions of years ago. It might have been born in the burning heart of a distant star, or in a swirl of dust as old as creation itself. Every photon touching you now has been travelling since long before the first trees grew, before the first humans breathed, before the world even had names for light and shadow. But what is a photon, really? You could say it's a particle, but also a wave. You could call it energy in motion. Scientists like to describe it as a quantum of light, a single packet of brightness that can act both like a grain of sand and like a ripple in water. Yet these are just words, ways to measure and predict. For our quiet story tonight, think of a photon as something simpler, a traveller, a wanderer who carries the memory of where it began. In the heart of a star, atoms collide in endless dances, hydrogen becoming helium, releasing tiny bursts of energy each time they fuse. Out of that release comes light, not one colour, but all colours at once, woven together into a single invisible hum. These newborn photons are restless. They want to escape. But the star is dense, filled with layers of gas and plasma. So before one photon can leave the surface, it bounces, not once or twice, but millions upon millions of times, like a thought trying to find its way out of a crowded mind. It can take thousands, even hundreds of thousands of years for that one bit of light to finally break free and begin its long journey through the cosmos. When it does, something quiet and astonishing happens. It travels straight, endlessly, and at a speed beyond imagination. The fastest thing the universe allows. And yet, even while moving so quickly, it gathers memories. Not like our memories of faces or sounds, but through subtle changes in its colour, its rhythm, its energy. As light travels, the universe itself stretches. The distance between galaxies grows, and that stretching gently pulls on the light too, lengthening its waves. Scientists call it redshift. But you can imagine it as the way a sound lowers when it drifts away, a kind of cosmic sigh. Each photon carries that deepening colour as a record of the journey it's taken. The farther it travels, the redder it becomes, as though the universe itself is tinting its diary pages with the ink of time. Some of the light we see from the most distant galaxies has travelled for over 13 billion years. It is the colour of patience, the soft rust of eternity. Along the way, these photons cross invisible seas of matter, clouds of hydrogen, drifting dust, magnetic fields, and the faint pull of gravity from stars and planets they pass. Each encounter leaves a trace, a tiny bend in their path, a whisper of lost energy, a subtle change in direction. It's as if space itself is writing notes in the margins of light's long story. Sometimes light doesn't even travel freely. Near something massive, a star, a black hole, or an entire galaxy, gravity bends the path of photons. They curve, they slow down just a little, and time itself shifts around them. Einstein predicted this, and later we saw it happen. Light doesn't resist, it simply adjusts, gracefully following the curve of space as though it were gliding along a river's bend. Even this bending, this slowing, becomes part of light's memory. A small delay, a different angle, a gentler tone. All clues for those who know how to read them. You could think of the universe as a vast library, with light as its ink. Every star, every nebula, every distant burst of radiation writes a line in that library. And as these photons move through the cosmic corridors, they keep those words intact, carrying them across billions of light years to our eyes, our telescopes, and sometimes even to the back of your eyelids when you look up on a clear night. When light finally reaches us, we're not just seeing what is, we're seeing what was. Every glance at the night sky is an act of time travel, your eyes catching messages that began their journey long before humanity existed. The faint light of the Andromeda Galaxy left its home when our ancestors were just discovering fire. The glow of the cosmic background, the oldest light we know, began its trip when the universe was still shrouded in mist. And yet, light never complains about distance. It never forgets the way. It simply continues, steady, faithful, unchanged in its purpose. Through its colour and rhythm, through its gentle shifts and curvatures, light records everything. It is both messenger and memory. So the next time you stand beneath the stars, remember, those tiny sparks are not just decorations in the sky. They are stories. Stories of heat, of gravity, of time itself stretching like silk in the wind. You're standing in their glow, reading what they have carried since the dawn of everything, a soft, radiant whisper from the past. If you could stand inside a star, not on its surface but deep within its blazing heart, you would find a world both violent and delicate. There, everything is movement. Atoms collide, fuse and change shape under unimaginable heat and pressure. Hydrogen, the simplest of all elements, a single proton and a single electron, meets another and transforms into helium. In that instant, a tiny portion of their mass vanishes, turning into pure energy. That energy is released as light, a flood of new photons born from the union of matter itself. This is how nearly every beam of light we see begins, as a byproduct of creation, a whisper from fusion's fire. Yet the journey from that birth to the space beyond the star's surface is not swift. The star's interior is so dense that a newborn photon cannot move in a straight line. It travels only a few millimeters before it is absorbed by another atom, then re-emitted again in some random direction. Imagine trying to leave a crowded ballroom where everyone is dancing wildly and bumping into you from every side. That is what it feels like for a photon trying to escape a star's core. Each absorption and re-emission changes the photon just a little. It may lose a touch of energy, shift its colour slightly toward red, or scatter into a new direction. For hundreds of thousands of years it repeats this pattern, absorbed, released, absorbed again, bouncing in a ceaseless game of cosmic pinball. And so, although a photon moves at the ultimate speed allowed by nature, the time it takes to emerge from the star's depths could exceed the span of human civilization. Inside the star, light is both restless and trapped. When at last a photon nears the surface, something changes. The density thins, the gas grows clearer. With one final leap, it breaks free. It leaves behind the pressure, the collisions, the fiery cradle of its birth, and bursts into open space. That moment, the first instant of freedom, is when a photon becomes a traveller. From then on, nothing can stop it. It will never slow down, never tire, never grow old. It may scatter, bend, or fade, but its speed remains constant, about 300,000 kilometers each second. We call that number the speed of light, but you can think of it as the universe's heartbeat, the pace at which information, warmth, and memory flow through the cosmos. Not all photons begin in stars. Some are born in the quiet chill of space itself. Long before the first galaxies formed, when the universe was still a glowing mist, matter and radiation danced as one. At that time, about 380,000 years after the beginning, the cosmos cooled just enough for protons and electrons to join and form the first atoms. When they did, the fog of charged particles cleared and light was finally able to travel freely. Those ancient photons still exist today. We know them as the cosmic microwave background, a faint glow filling every corner of space. You could call it the universe's baby picture, a frozen image of the first moment light escaped darkness. Every photon from that time carries with it a record of the young universe, its temperature, its density, its first ripples and imperfections. When we map that faint light, we are reading the oldest memory ever recorded. Each slight change in brightness on that cosmic background tells us how matter first began to gather, how galaxies would one day form, and how the seeds of every star, even our own sun, were planted. There are other kinds of light births too, smaller and closer to home. When you strike a match, the chemical reaction between sulfur and oxygen releases energy in the form of heat and light, a sudden miniature sunrise in your hand. When lightning flashes, the movement of electrons through the air excites atoms that release photons as they calm again. Even the glow of your phone screen is a cascade of engineered photons, coaxed into colours by precise electric pulses. Every light you see, from candle to supernova, is an echo of the same principle, energy becoming visible. But perhaps the most poetic birth of light happens in the moments of destruction. When massive stars die, their cores collapse and the outer layers explode in a brilliant supernova. For a few days, one dying star can outshine an entire galaxy. In that explosion, elements heavier than iron are forged, and the light released can travel across the universe for millions of years. Some of the atoms in your body, the iron in your blood, the calcium in your bones, were once part of a star that ended this way, scattering its light and matter together. In a sense, you are made from ancient photons that have turned solid. It's comforting in a quiet way to think of every photon as part of this endless cycle. Birth in fire, journey through darkness, sometimes captured by matter, sometimes freed again. Even the light that reaches your window each morning has travelled through this cosmic lineage. It began in the sun's core long before you were born, wandered upward for ages, crossed the empty space between worlds in just 8 minutes, and finally fell onto your face as warmth. In that moment, you are not merely being illuminated, you're receiving a message that began its journey thousands of centuries ago. And though we talk about speed and energy and wavelength, these are only human measures of something that feels much older than our numbers. You could think of a light's wavelength, the distance between one crest and the next, as its rhythm, its heartbeat. Red light has a longer rhythm, a slower pulse. Blue light has a faster, sharper one. Together they form a silent symphony, every photon humming in its own tone, composing the grand music of the cosmos. When those rhythms change, stretched by distance, compressed by motion, They are not equations on a page, but the living memory of travel itself. So when we speak of formulas like E equals h times f, the energy of a photon equals a constant times its frequency. Let's translate that into something gentler. It means that the faster a photon vibrates, the more energy it carries. Imagine tapping a drum. A slow beat gives a deep, warm sound. A quick beat gives a sharp, bright one. Light works much the same way. The universe keeps its rhythm through these vibrations, and every change in tempo tells us a story about where the photon has been. From fusion in a star's heart to the pale afterglow of the early universe, from the spark of a match to the flash of a dying sun, every photon begins as an act of transformation. Matter becomes energy, chaos becomes clarity, and darkness becomes something we can see. Each photon is a note in the universe's memory, carrying a trace of its birthplace, its journey, and perhaps, in a way we're only beginning to understand, a memory of us, the beings who, billions of years later, would open our eyes and try to listen. When a photon finally escapes the surface of its star, it doesn't pause or look back. It begins a journey that will last for millions, even billions of years. A journey without a map, without rest stops, and without the need for fuel. It doesn't think, but if it did, perhaps it would marvel at the vastness ahead. A sea of emptiness speckled with distant suns, veiled clouds, and invisible rivers of gravity that quietly bend its path. From the moment of release, that photon is free, yet space itself is not still. The universe is stretching gently and continuously. You can picture space as a vast fabric that expands while everything within it drifts apart, like dots on an inflating balloon. As this fabric stretches, the waves of light stretch too. Their crests drift farther apart, turning the light redder and softer. Astronomers call this redshift, but you could imagine it as the way a song slows when the record spins down, the same tune played at a gentler tempo. That softening of light is one of the universe's most eloquent memories. The farther a photon travels, the more its wavelength grows, and, by measuring that stretching, we can tell how much the cosmos has expanded since the photon began its journey. Each beam of light, then, is a time capsule, not only of where it came from, but of how much the universe itself has changed along the way. The light that reaches us from a nearby star is a letter written just a few years ago. The light from the Andromeda galaxy left its home over 2 million years ago, when early humans were shaping stones and lighting their first fires, and the faintest glimmers that our telescopes detect, light from galaxies at the edge of visibility, set out when the universe was still young and full of fog. Every time we look deeper, we look further back. It's as if space itself has turned into a hallway of mirrors, each reflection showing an older, dimmer version of reality. But light's road is not perfectly smooth. There are clouds along the way, not of water, but of hydrogen gas, dust grains, and magnetic fields that fill the interstellar and intergalactic medium. These are the hidden landscapes of space, invisible to our eyes but tangible to light. When a photon passes through one of these regions, it can scatter or lose a bit of energy, just as sunlight softens when it filters through smoke or fog. Sometimes entire wavelengths are absorbed by atoms in the gas, leaving dark lines in the spectrum, like letters missing from a word, each gap telling a story about what the light encountered. The intergalactic hydrogen is particularly talkative. Its single electron can jump between two energy states, and when light of just the right wavelength passes through, the electron absorbs it and then releases it again in a slightly altered direction. This creates a forest of delicate absorption lines in the light from distant quasars, known to scientists as the Lyman Alpha Forest. You could think of it as a trail of fingerprints, each one marking the spot where the photon brushed against the ancient fog of the universe. Through these tiny shadows, astronomers can map the invisible web that connects galaxies across billions of light years. As the photon continues, it meets another sculptor, gravity. Though we often imagine light as perfectly straight, gravity can bend it. Wherever there is mass, a star, a planet, or a cluster of galaxies, space itself curves around it, and light follows that curve. From far away, this can make a single object appear in several places at once, like one candle reflected in many mirrors. This bending is called gravitational lensing, but to the photon, it is simply the shape of its road. When we study these curves, we're not only learning about the object the light came from, but also about the unseen matter, dark matter, that shape the road itself. Sometimes the pull of gravity slows light just a little as it passes through deep wells of mass. This slight delay, called the gravitational time lag, is invisible to the eye but measurable in the patient. Language of physics, you might imagine light sighing as it climbs out of a gravitational valley, giving up a touch of its energy to escape. That lost energy becomes another note in light's long melody of memory. And yet, even as light bends and softens, it never stops. It keeps moving, faithful to the rhythm set at its birth. When it finally reaches a telescope, perhaps on a mountaintop or orbiting high above Earth, it is caught gently by a mirror. There, the journey ends, but not the story. We study its colour, its faint flicker, its pattern of absorption lines, and through these details we reconstruct the entire voyage. Each photon is like a letter that has crossed 1 billion years, folded and refolded by dust and gravity, yet still legible when opened by the right reader. In its quiet way, light carries the memory of everything it has touched. The deep red of a galaxy's light tells us how far it has travelled and how much the universe has stretched since it left. The small distortions in its path reveal the presence of dark matter, unseen but heavy. The faint polarization, the direction in which the photon's electric field vibrates, carries the signature of magnetic fields it passed through. These are not formulas on a chalkboard. They are the diary entries of the cosmos itself, written in light. If you wanted to describe this story mathematically, you could write that energy equals a constant times the frequency of the photon. But here, let's think of it differently. The higher the note of the light, the faster its vibration, the more energetic it is, just as a high-pitched sound feels sharper and livelier. As the universe expands, that note slows, deepening into a redder tone. What we call a frequency shift is simply the universe changing key, its music lowering as it grows older. Some photons never make it to us. They might be absorbed by dust and turned into warmth, re-emitted as longer, softer waves of infrared light. Others may be caught in the magnetic arms of galaxies or scattered endlessly through the fog of interstellar space. But even those lost travellers still carry their memories forward, rewritten in new wavelengths, new forms. Nothing of light truly disappears, it only changes voice. And perhaps that's what makes light such a perfect storyteller. It adapts to the medium, the moment, the scale of time itself. Whether travelling across a few centimetres or the whole observable universe, its message remains. Everything leaves an imprint. When you open your eyes and see the faint shimmer of a star, you're catching one tiny echo of this grand symphony, a note that has travelled across time and distance to arrive here, in this single, quiet instant. Light never stops moving, and yet in each of its colours it pauses just long enough for us to read. In every hue, in every soft vibration, there is the story of where it has been, the long road home, still unfolding before our eyes. Resistimon. There is a kind of light that has been travelling since almost the beginning of everything. It fills every corner of the universe, not in bright beams or sharp colours, but as a faint, patient glow. It doesn't come from stars or galaxies, it comes from a time before there were any. This light is called the cosmic microwave background, though you might think of it more simply as the afterglow of creation, the first photograph the universe ever took of itself. To understand why this light exists, we need to go back, not just far in space, but deep in time, about 13.8 billion years. In the beginning, everything was compressed into a hot, dense mist where light couldn't travel freely. It was as though the cosmos were a vast fog of energy, where particles of matter and light were so tightly intertwined that neither could move without colliding with the other. Photons bounced endlessly off free electrons, never able to escape. The universe, in its youth, was bright but blind, glowing everywhere, yet transparent nowhere. But expansion is the universe's habit. With every moment, space stretched and cooled. The temperature fell from trillions of degrees to thousands. Then, after roughly 380,000 years, a quiet miracle occurred. The fog began to clear. The heat dropped enough for electrons to settle down and join protons, forming the first simple atoms of hydrogen and helium. The moment they did, light was freed. No longer scattered at every turn, photons could finally move unhindered. They began their journey outward, in every direction, from every point in space, and they have never stopped since. That first release of light is what we see today as the cosmic microwave background, or CMB. It's not bright to our eyes because billions of years of expansion have stretched its colour into a deep, invisible red, wavelengths so long that only sensitive radio instruments can detect them. Yet it's everywhere, bathing us quietly like the memory of a long-faded fire. If you could tune an old television to an empty channel and watch the static snow on the screen, about 1% of that noise would be this ancient light, the literal echo of the Big Bang. What does this ancient glow tell us? Quite a lot. Embedded in that faint radiation are tiny ripples, temperature variations of just a few millionths of a degree. They may seem insignificant, but they are the fingerprints of the infant universe, the earliest record of the forces that would shape everything to come. Where the light was slightly warmer, matter was slightly denser. Gravity drew more matter in, forming the seeds of future galaxies. Where it was cooler, space expanded a bit faster, thinning the material and leaving behind cosmic voids. The entire large-scale structure of the universe, every cluster, every galaxy, every star, traces back to those gentle ripples frozen into the CMB's light. Scientists sometimes describe the pattern of these ripples using harmonics, a word that might sound mathematical but really means something musical. You can imagine the early universe as a kind of cosmic drum, vibrating with waves of pressure and sound. Those waves left their marks in the temperature patterns of the CMB, a visual symphony recorded in light. When researchers plot these patterns, they see peaks and valleys like notes on a staff, each one telling us about the density, composition, and age of the universe. The equations may look complex on paper, but what they really describe is the first song the universe ever sang, a deep hum that still resonates in the silence of space. If we were to translate that data into something our senses could understand, it might sound like a faint, steady tone, a note that has been playing for nearly 14 billion years. It doesn't change key, but it grows softer as the universe expands, its pitch lowering with time. This is the hum of existence, a constant reminder that the cosmos remembers its own birth through the music of light. This CMB also tells us about time itself. By measuring its faint glow and its slight unevenness, we can estimate how fast the universe is expanding, how much matter and energy it contains, and even how old it is. In a way, these photons serve as cosmic archivists, recording the conditions of their era in the language of temperature and wavelength. They are not conscious, of course, but their very nature allows us to reconstruct the ancient past with astonishing precision. It's as though the universe left us a diary written in the ink of light, and the diary has layers. When we look at the CMB, we're not only seeing temperature, we're also seeing polarization, a subtle orientation in the way the light waves vibrate. That orientation carries clues about the moment when the first stars and galaxies began to form, hundreds of millions of years later. As those early structures lit up, they sent out bursts of radiation that gently reionized the surrounding hydrogen gas, leaving new imprints on the old light passing through. The CMB, therefore, is not a single snapshot but a palimpsest, an ancient page written, rewritten, and annotated across cosmic time. There's poetry in the idea that we can still see the glow of an event that happened so long ago. When telescopes like Planck or Doppler map the CMB, they're essentially photographing the oldest visible surface of the universe, a sphere of light surrounding us from every direction. We're not at the centre because of any special importance. It's simply that wherever you stand, the ancient light reaches you from the same distance away. Each point in space has its own horizon of memory. Sometimes people wonder, if that light has been travelling for nearly 14 billion years, what has happened to the place where it began? The answer is both simple and strange. The matter that once emitted that light has long since moved, forming stars and galaxies far away. The photons we receive now were never aimed at us. They simply left in all directions, and by the geometry of the expanding universe, some happened to arrive here. What we see in the CMB is therefore not a picture of a distant object, but a picture of the universe itself, when it was young, glowing, and newly transparent. Imagine standing in a dark room, lighting a match, and then letting the smoke and heat drift away. Long after the flame goes out, the warmth lingers in the air. That lingering warmth is what the CMB is to the cosmos. A remnant glow, a gentle warmth from a fire that has long since faded. Even though the temperature of this light is now just a few degrees above absolute zero, it still holds the memory of a time when the entire universe blazed with brilliance. Every photon of that ancient background has travelled a nearly unimaginable distance to reach us. Along the way, it has been stretched, cooled, and ever so slightly bent by gravity. Yet it still carries its original signature, the story of its release into freedom nearly 14 billion years ago. When we detect those photons today, we are literally touching the oldest light that exists, the first whisper of visibility in a once blind cosmos. And so, when you look up at the night sky, filled with modern stars and galaxies, know that behind them lies this older, softer light, a veil of memory spanning the entire universe. It's the quiet photograph of everything that was, long before there were eyes to see or minds to wonder. The CMB is not just data, it's a cosmic lullaby, the faint hum of time itself remembering its own beginning. There's a quiet strangeness to light. It has no mass, no weight to speak of, and yet it feels the pull of gravity. The same force that keeps our feet anchored to the ground can bend a beam of light, twist its path, and even delay its arrival. In a universe ruled by curves rather than straight lines, light must learn to walk softly through gravity's invisible landscape. If space were perfectly flat, photons would glide endlessly in straight, unwavering paths, like arrows shot through still air. But space is not flat. It bends and folds wherever mass exists. A planet, a star, or a cluster of galaxies doesn't just sit in space. It reshapes the space around it. Einstein once described this with a gentle metaphor. Mass tells space how to curve, and space tells matter how to move. That simple idea changed everything, revealing that what we call gravity is not a force pulling downward, but a bending of the stage itself. Light, obedient to the structure of space, follows these curves. Imagine rolling a marble across a soft fabric stretched tight, and then placing a heavy ball in the middle. The fabric dips, and the marble's path curves as it moves around the depression. Now imagine that marble is a photon, and the fabric is space-time itself. When the photon passes near something massive, a star, a planet, or a cluster of galaxies, it follows the dip, gliding along the curve before straightening again. To us, far away, it looks as though the light has bent, as though gravity has reached out and tugged at it. But in truth, light is only following the geometry of the universe. One of the most beautiful consequences of this bending is something called gravitational lensing. When light from a distant galaxy passes through the warped space around another galaxy or a cluster, the bending can focus and magnify the light, much like a glass lens does. Sometimes it creates duplicate images of the same object, a cosmic mirage where one galaxy appears as 4, 5, or even a perfect ring of light. These rings are known as Einstein rings, though you can think of them more gently as ripples frozen in space. Through these lenses, light tells us two stories at once. First, it shows us the galaxy behind the lens, the original source of the light. But it also reveals the hidden mass of the lensing object itself. Because light bends in proportion to how much mass lies in its path, scientists can use these distortions to map the otherwise invisible. This is how we discovered that most of the universe's matter is not the kind we can see. It doesn't shine or absorb light, yet its gravity betrays it. We call it dark matter, though unseen matter might be kinder, for light has shown us its presence even when the thing itself stays silent. Gravity's influence on light doesn't end there. It can change not only direction, but also the rhythm of light, its frequency, its pitch. When a photon climbs away from a massive object, it loses a bit of its energy. Its colour shifts slightly toward red, as though the climb has slowed its heartbeat. This is known as gravitational redshift, but in softer terms, you could say the photon grows weary as it leaves a deep valley of gravity. The deeper the valley, the greater the fatigue. In the heart of a black hole, that valley becomes so deep that not even light can escape. The edge of no return, where light stalls forever, is called the event horizon. There, the flow of time itself slows to stillness. For photons that do escape such gravity wells, their exhaustion becomes part of their memory. By measuring how much their colour has changed, astronomers can tell how strong the gravity was where they began their journey. It's as if the photon carries a faint bruise from the weight of the world it left behind. Sometimes, the story is written not in colour, but in time. Light passing near massive clusters takes slightly longer to reach us than light travelling through emptier regions of space. The detour, the climb through warped geometry, adds tiny delays, measurable differences in arrival time between photons coming from the same source by different routes. These time delays have become one of our most precise cosmic clocks. By comparing them, scientists can estimate the universe's expansion rate, how far space itself stretches over time. What began as a curiosity about light's behaviour under gravity has become one of the sharpest tools for understanding the scale and age of everything. But beyond the calculations, there's a quieter truth. Gravity teaches light to be graceful. No matter how extreme the curve, light adapts. It bends without breaking, delays without complaint, and always continues forward. Even when distorted into arcs or stretched into rings, it preserves the essence of its story. Each photon that reaches us after weaving through cosmic valleys brings with it a testimony, proof of how space has shifted, of how mass has gathered, of how time has flowed. We see this in the photographs of distant galaxies wrapped in arcs of blue and gold, their light stretched into ribbons by gravity. In those images, the universe becomes both mirror and map, each curve of light tracing the shape of the unseen. What was once invisible becomes knowable, simply because light was willing to take the long way around. There is something deeply human in that. We too are shaped by the forces we pass through. Our paths bend around memories, around people and moments that pull at us like gravity wells. We take detours, we slow down, we stretch, yet we carry the record of it all in who we become. Light does the same. It carries its distortions as part of its truth. Even the tiniest delay, the smallest bend contains meaning. The faint change in tone that reveals the pull of gravity near a star. the split image that hints at hidden matter, the slow red drift that tells of energy lost. These are not just measurements. They are the handwriting of the cosmos. When we decode them, we are not imposing our understanding on the universe. We are listening to what light has already remembered. The next time you see a photograph of an Einstein ring or a faint galaxy magnified by another's gravity, try to picture the journey that light took to reach us. Picture it gliding along curved space, its path bending softly like a reed in the wind. Imagine the patience it takes to cross billions of years, to detour around galaxies, to arrive just so that we might glimpse its story. In the end, light doesn't resist gravity, it harmonizes with it. Space bends, and light dances to the tune. And through that dance, the universe paints portraits of its own invisible architecture. Gravity may curve the road, but light ensures we never lose sight of where it leads. Far beyond our galaxy, where space turns thin and the light of stars begins to fade, there exists a quiet mist, invisible to our eyes, but real enough to change the way light remembers its journey. This is the intergalactic medium, a vast sea of hydrogen gas stretched between galaxies. It's not dense like a cloud, but rather a delicate haze, a few lonely atoms drifting in each cubic meter of space, and yet, over cosmic distances, even that faint mist leaves its fingerprints on light. When a photon passes through these ancient vapours, it sometimes loses a bit of itself, a tiny fraction of its energy absorbed by the atoms it meets. Each time that happens, a specific colour disappears from the spectrum of light. To the naked eye, it's invisible, but through the lens of a spectrograph, it looks like a small dark notch, a missing note in the cosmic melody. Over billions of years, as light passes through countless pockets of hydrogen, these notches multiply and spread, forming what scientists call the Lyman alpha forest. But don't think of this forest as a physical place with trees and leaves. Think of it as a map made of shadows, each shadow marking where light was touched by matter. The pattern of these tiny gaps is like the whisper of the universe between galaxies, the soft conversation of atoms that never formed stars, never gathered into worlds, but still linger in the great dark between. Imagine for a moment the light of a quasar, a distant, furious beacon powered by a black hole's hunger. It shines across billions of light years, so bright that it pierces the entire cosmos. As its photons travel toward us, they weave through those invisible mists of hydrogen. Each cloud leaves a mark, removing one particular colour of light, corresponding to a wavelength near the edge of ultraviolet. If you could unroll that beam and lay its colours side by side, you'd see a delicate barcode of absence, a forest of missing hues stretching across the spectrum. Each of those missing lines tells us something. The deeper the notch, the thicker the gas. The redder its position, the farther away the cloud was when the light passed through it, because as the universe expands, the light's wavelengths stretch, shifting each mark toward the red part of the spectrum. By reading these patterns, astronomers can reconstruct the large-scale structure of the cosmos, not the bright galaxies themselves, but the filaments of gas connecting them like the faint veins of a leaf. It's through these dark gaps, not the luminous stars, that we glimpse the true skeleton of the universe. And here is something quietly profound. The more distant the quasar, the denser its forest of shadows. There comes a point around the era when the first galaxies were born, where the gaps merge into one vast dark trough. This is known as the Gunn-Peterson trough, but rather than remembering the name, think of it as the moment the dawn broke on cosmic history. It marks the time when the early universe transitioned from opaque to transparent, when the first stars and galaxies ionized the fog, clearing the path for light to travel freely once more. It's the universe's second sunrise, written in shadow instead of flame. In the soft language of science, the interaction that causes these shadows is described as an electron in a hydrogen atom jumping between two energy states. But spoken gently, it's simpler than that. When a photon of just the right energy comes along, the atom pauses it, absorbs it for the briefest instant, and the electron inside leaps to a higher level of excitement. Then the atom releases the photon again, but now it goes off in a new direction, its path changed forever. Multiply that by billions of atoms across the cosmic ocean, and you have the quiet dance that sculpts the Lyman alpha forest. Through these subtle patterns, light remembers where it has wandered. We read that memory by decoding its shadows. To a spectrograph, those shadows are data, but to a storyteller, they are the faint traces of encounters, each one a handshake between light and matter across unimaginable distance. Even the tiniest variations in those absorption lines can reveal the temperature and motion of the gas clouds. When a cloud is warmer, its atoms move faster, blurring the lines a little. When the cloud is drifting toward or away from us, the lines shift slightly to blue or red, the same effect you hear when a passing train changes pitch. The universe hums with that same Doppler rhythm, and the photons carry it faithfully. As our instruments grow more sensitive, we begin to see not just the forest, but the whole ecosystem within it. There are regions where the lines cluster densely, the seeds of future galaxies, and others where they thin out into great empty voids. Some of the light absorbed there is re-emitted later as faint glows of hydrogen, allowing us to trace the flow of matter through space like ink spreading through water. It's astonishing to think that something so intangible, a slight change in colour, can reveal the architecture of everything that exists. You might wonder how such delicate features survive the long voyage through expanding space. After all, these photons have travelled for billions of years, stretched and cooled by cosmic expansion, bent by gravity and scattered by dust. Yet the pattern remains, preserved like fossils pressed into the strata of light. The Lyman alpha forest, in that sense, is both a map and a memory, an unbroken record of the universe's in-between places, where nothing shines but everything matters. When you gaze at a photograph of a quasar's spectrum, with its forest of thin black lines, you're looking at one of the most direct forms of cosmic storytelling. Each line began as a collision, a brief meeting between light and gas in the distant past. Those encounters, multiplied across the universe, become a script that we can still read today. It's humbling to realise that what we call empty space is anything but empty. Between the bright islands of galaxies lies a sea of quiet structure, rivers and filaments of gas gently sculpted by gravity threaded through the dark. Light doesn't ignore this space, it listens to it, interacts with it, and carries its story forward. The forest of shadows, then, is not a sign of absence, it's a sign of connection, the proof that even in the deepest silence the universe leaves traces of its conversation. If you were to translate the scientific equations describing this phenomenon, they would speak of wavelengths, energy levels, and absorption probabilities. But what they truly describe is something far simpler and more beautiful. The way light slows just long enough to greet what it passes. It's as if the photon, eternal traveller that it is, occasionally pauses to shake hands with the atoms of the universe, then continues on, carrying that gentle exchange as part of its long memory. And so, even the darkness between galaxies is not void but story, a record of where light has been, written in the faintest of lines. We may never visit those places, but through the patient reading of these shadows we know they are there. The forest of light's memory stretches in every direction, and we, tiny creatures bound to one small world, stand here among the leaves, reading the patterns of a universe that remembers everything it touches. In the great inventory of the cosmos, something once appeared to be missing. For decades, astronomers counted the stars, the galaxies, the gas clouds, and the glowing filaments of matter that stretch between them, and still the numbers didn't add up. According to our understanding of how the universe began, there should have been more ordinary matter, the kind made of protons, neutrons, and electrons, the building blocks of everything we touch. Yet when scientists tried to account for all of it, almost half had vanished. These were the called lost baryons, a name that simply means the missing portion of the universe's normal matter. They weren't dark matter, which doesn't interact with light at all, nor dark energy, which drives cosmic expansion. These missing baryons were supposed to be normal, visible stuff, just unseen. Somewhere between the galaxies they had gone quiet, slipping out of sight but not out of existence. The mystery lingered until, quite unexpectedly, light itself, or rather a special kind of light, began to whisper their location. Not the familiar light of stars or galaxies, but the quick staccato bursts of radio waves that astronomers now call fast radio bursts, or FRBs. Each one lasts only a few thousandths of a second, shorter than the blink of an eye. Yet in that instant it releases as much energy as the sun emits in days. No one yet knows for certain what causes them. Some may come from the collapse of massive stars into neutron stars, others from magnetars, those strange ultramagnetic remnants that crack and flare like cosmic nerves. But whatever their origin, FRBs are loud enough to be heard across billions of light years, and in their brightness lies a clue far more valuable than their mystery. When these bursts of radio light travel through space, they don't all arrive at once. The higher-pitched, faster oscillating waves reach us first, the lower tones lag behind. It's as if the universe was stretching the sound of a single bell into a descending chime. This delay happens because the radio waves pass through clouds of free electrons scattered throughout space, and each electron slightly slows the lower frequency part of the signal. The more electrons there are between the source and us, the greater the delay. Scientists call this pattern dispersion, though you can think of it as the way fog muffles a sound. The thicker the fog, the longer it takes for the softer notes to reach you. By measuring this difference in arrival times, astronomers can estimate how many electrons, and therefore how much ordinary matter, the light passed through. When researchers began cataloguing FRBs and comparing their dispersion to the distances of their host galaxies, a remarkable pattern emerged. The numbers lined up perfectly with what theory had predicted decades ago for the missing matter. Every lost baryon, it seemed, was hiding in plain sight, not gone, just thinly spread throughout the vast, hot space between galaxies, in what's known as the warm-hot intergalactic medium. The relationship between the amount of delay and the distance of each FRB became so consistent that scientists named it the Macquarie relation, after the astronomer who helped reveal it. But stripped of its academic name, what it really represents is one of light's most astonishing acts of remembrance. Each radio burst, while rushing across the universe at the speed of light, kept a record of the invisible electrons it brushed past. Every tiny nudge, every whisper of plasma along the way. By the time that light arrived at our telescopes, it had encoded an entire map of the cosmos's missing matter within the faint stretch of its tone. If you could hear it rather than see it, an FRB would sound like a cosmic flute note descending through invisible air, its pitch sliding lower and lower as it journeys through space. That change in tone is not random. It's a signature, a memory of everything the light has touched. Through that melody, the universe finally confessed where it had hidden half of its material self. The precision of this cosmic memory is breathtaking. Imagine you toss a handful of sand across a desert and then, years later, listen to the echo of a single shout and can tell exactly how many grains it passed over. That's what scientists do with these millisecond flashes. The delays, measured in fractions of a second, reveal the total number of electrons along billions of light years of travel. It's a kind of mathematics, yes, but one that speaks through rhythm and timing rather than symbols and formulas. To make sense of the numbers, astronomers translate them into density. How many atoms fill a certain volume of space? Instead of equations, we can imagine it this way. For every cubic meter of intergalactic space, there are just a handful of lonely particles fewer than you could count on one hand. Yet when those few are stretched across the infinite ocean between galaxies, they account for nearly half the matter we once thought was gone. Light, passing through, finds every one of them. These discoveries have turned FRBs into a new kind of cosmic probe. With each burst, we can weigh the invisible, trace the filaments of plasma threading between galaxies, and even test how gravity itself behaves over vast distances. Some scientists have begun to dream that, in time, these radio whispers might help us map the universe with exquisite precision. Not by what shines, but by what delays the shining. There's something poetic about the idea that the universe keeps track of itself through lateness. A photon that arrives late is not failing, it's telling us where it lingered. The very act of being slowed becomes a form of communication. It's a reminder that patience, even on a cosmic scale, can reveal hidden truths. If you could picture these FRBs visually, they'd look like sparks flickering across the sky, each one a brief flare of pure information. But what matters most is not the flash itself. It's the soft trail of delay behind it, the memory encoded in the time it took to get here. Each burst becomes a messenger from the in-between, the unseen web connecting all things. And perhaps there's something familiar about that. In our own lives too, meaning often lies in the pauses, in what takes time to reach us. The universe, it seems, operates on the same principle. It doesn't rush to show everything at once. It lets light wander, delay, and change, so that by the time it arrives, it carries not just brightness, but understanding. The missing half of the universe's matter was never truly lost. It was simply waiting for us to learn how to listen. And all along, light had been keeping the record, stretched across time, scattered across space, humming faintly in radio tones that drift like wind through intergalactic emptiness. The photons did what they have always done. They remembered. So the next time you hear a burst of static from a distant source, that sharp hiss in a radio telescope that lasts no longer than a heartbeat, imagine that you're hearing the sound of the cosmos counting itself, one electron at a time. Each whisper is a testament to the completeness of light's memory. It forgets nothing, not even what we once thought was gone. If you could drift silently between the galaxies, you would see that space is not empty. It hums with heat, faint but everywhere. Between clusters of galaxies lies a ghostly sea of electrons and ions, the residue of stars long dead, the scattered breath of cosmic explosions, and the faint shimmer of gases falling through gravity's hands. This plasma, though invisible to human eyes, glows brightly to light that can feel it. The photons from the ancient cosmic background, the ones born nearly 14 billion years ago, pass through these clusters and come away changed, warmed ever so slightly, as if brushing against the memory of fire. This encounter is known to astronomers as the Sunyaev-Zeldovich effect, named after the two scientists who first described it. But the name is less important than the story it tells. When an ancient photon meets a cloud of hot electrons, the kind that fill galaxy clusters, it scatters off them. In that tiny collision, the photon gains a small push, a flicker of extra energy. It becomes a little bluer, its wavelength a touch shorter. The change is minute, far beyond what our eyes could see, but when millions of such photons are measured together, the pattern reveals itself. It's as though the light has picked up a faint blush from the heat it encountered, carrying with it a record of that warmth across the void. To understand why this matters, imagine a single galaxy cluster, a collection of hundreds, sometimes thousands of galaxies bound together by gravity. The space between those galaxies is not dark. It's filled with a thin mist of gas heated to tens of millions of degrees, hot enough that atoms can't hold on to their electrons. Those freed electrons drift like restless spirits, scattering any photon that crosses their path. Each encounter changes the photon's colour just a little, a conversation between light and matter that leaves an imprint on both. When we map the sky in microwaves, we can see these subtle temperature shifts as small dimples or bright spots against the smooth background of the cosmic microwave glow. Each one marks the position of a galaxy cluster, even if the cluster itself is too distant or faint to see in visible light. Light, having passed through, tells us what lies hidden. It remembers where it was warmed and by how much. There are two versions of this effect, and each reveals a different story. The first is the thermal version, the one that records heat. It shows us how energetic the gas is inside clusters, allowing astronomers to weigh the clusters and trace how matter gathers through cosmic time. The second is the kinetic version, a whisper of motion. As a cluster drifts through space, the light passing through it gains or loses a little energy, depending on whether the cluster is moving toward us or away. It's the cosmic equivalent of the Doppler shift you hear, when an ambulance siren changes pitch as it passes by. But instead of sound, it's the pitch of light itself, a change so delicate that only the universe's most patient instruments can detect it. Together, these two effects let us read the motions and temperatures of structures billions of light years away. Through them, we've learned that clusters are not still islands but living, breathing systems. They collide, merge, and spin. Their gas is stirred by gravity and shock waves like eddies in a vast ocean. Every collision heats the gas, and every photon that travels through carries away a trace of that warmth, a signature of motion frozen into the light. To speak about this in the language of numbers, scientists would say that a photon's energy changes by a fraction equal to the temperature of the electrons multiplied by a tiny constant that connects energy and frequency. But we can hear it more simply. When light passes through heat, it hums a little faster. Its rhythm quickens, like a heartbeat responding to excitement. The hotter the gas, the sharper the note the photon carries as it departs. It's a song of temperature, sung across billions of light years. What's remarkable is how consistent this memory is. Photons that left the early universe in perfect harmony return to us carrying tiny variations in tone. When we map those variations, we're effectively listening to the thermodynamic history of the cosmos. How matter clumped together, how gravity heated the gas, how galaxies were built. Every flicker of energy gained or lost tells us something about the structure of space itself. In recent years, astronomers have begun stacking thousands of observations together, combining the subtle signatures from many galaxy clusters to build detailed maps of cosmic heat. These maps are like thermal fingerprints of the universe, showing where matter has gathered, where collisions have flared, and where quiet stretches of space have cooled. It's a new way of seeing, not through brightness, but through warmth. And it's not only the big clusters that leave these imprints. Even smaller groups of galaxies, or the faint halos of gas surrounding individual galaxies, can warm the background light in detectable ways. Some researchers call this the missing link between galaxies and the vast web that connects them. Proof that the same gas which once hid the missing baryons now shapes the cosmic landscape in subtler, warmer tones. If you could see the universe through this lens, it wouldn't appear dark at all. It would shimmer with invisible heat, streaked with gentle gradients like watercolour brushstrokes. Every cluster would glow faintly against the background, each one a warm knot in the tapestry of space. Between them, cooler filaments of gas would weave the structure together, linking everything with the faintest of threads. Light passing through this tapestry doesn't erase it. It carries it forward, imprinting the memory of its warmth onto the background glow. There's something deeply moving about this idea, that even heat, something so fleeting and intangible, can be preserved in light's memory. The photons that left the early universe didn't know they would one day brush past galaxy clusters, pick up a trace of warmth, and bring it here to our detectors. But they did. The universe leaves no experience unwritten. Every encounter, every particle, every collision, every change in motion becomes part of the light that fills the cosmos. If you could hold a single photon in your hand, one that had crossed the universe, passed through clusters and voids, been nudged by gravity and warmed by heat, it would look no different from any other. Yet encoded in its vibration would be a story billions of years long, told not in words or numbers but in the gentle modulation of its rhythm. That rhythm, stretched and softened by time, reaches us now as a quiet signal, a reminder that nothing in the universe ever truly vanishes. The heat of galaxies, the dance of clusters, the motion of matter itself, all of it is recorded in the light that moves endlessly onward. So when astronomers look up and see the faint blushing of ancient photons, they are not just measuring energy. They are reading a diary written in warmth, a story of motion, of collision, of transformation. A story that reminds us that even in silence, the universe remembers the moments when it burned brightest, and keeps those memories glowing softly in the light that never stops travelling. In the quiet vastness of space, time does not flow in straight lines. It bends, stretches, and lingers in the hollows of gravity, like water slowing as it moves around a rock. Light, though the swiftest traveller we know, is not immune to these curves. Sometimes it takes the long way around, weaving through valleys of space-time shaped by galaxies and clusters, and in doing so it leaves us a curious kind of note. A delay, a difference in arrival time that tells of where it has been. These delays are not mistakes, they are memories written in seconds. Imagine a single quasar, a bright beacon powered by a black hole in the heart of a distant galaxy. Its light sets out in every direction, an ocean of photons racing outward through the expanding universe. On their way to us, some of those photons pass near another galaxy that happens to lie along the same line of sight. The gravity of that foreground galaxy bends the quasar's light into multiple paths, splitting it like a droplet refracting sunlight into separate colours. To our telescopes, the quasar now appears not as one image, but as 2, 4, or sometimes more. Identical flickers of the same source scattered across the sky. But these reflections do not all arrive at once. One beam might pass closer to the galaxy's centre, dipping deeper into its gravity well, while another travels around the outskirts. The deeper path curves more sharply, making the journey a little longer. When the quasar brightens or dims, as they often do, each of its lensed images changes at a slightly different time. The light is telling us, in its own patient way, how long it took to cross the uneven terrain of space. These small differences, sometimes days, sometimes weeks, are what astronomers call gravitational time delays. They are like echoes in a cathedral of galaxies, each one repeating the same song with a tiny pause. By measuring those pauses, scientists can learn the distances between objects, and even how fast the universe itself is expanding. It is as if the cosmos had built its own network of stopwatches, scattered among the stars, and light serves as both traveller and timekeeper. The key to this measurement lies in understanding the geometry of the paths. When light bends around a massive object, it must follow the curves dictated by Einstein's description of gravity. That mass distorts space and time itself. Each route that the photons can take has a different length and a different depth in the gravitational field. Because time flows a little slower in stronger gravity, the path that dips deeper into the well not only covers more distance but also experiences time differently. The combination of extra space and slower clocks results in a lag, a cosmic hesitation before the light finally reaches us. You might picture these pathways as threads stretched across a rippled fabric. Some threads run straight across the top, others sink into the folds, and a few loop around the deepest hollows. All eventually reach the same destination, our telescopes, but they do so in their own time. The beauty is that the light carries the memory of every curve it traced, and by comparing the arrival of each thread, we can reconstruct the shape of the fabric itself. This technique, called time delay cosmography, has become one of the most precise ways to measure the pace of cosmic expansion. The rate at which galaxies drift apart, known to scientists as the Hubble constant. The name may sound mathematical, but in gentle terms it is simply the tempo of the universe's breathing, the steady rhythm by which space grows. When astronomers study the delays between lensed images of a quasar, they are listening to that rhythm, counting the heartbeats of creation across billions of years. To extract that information, researchers model the intervening galaxy's gravity, tracing how it bends space and how those curves change the journey of light. No equations are needed here to imagine it. Think, instead of mapping the flow of a river through a valley, measuring how much longer it takes to reach the sea when the current must wind around mountains. Each difference in travel time becomes a measure of the landscape's shape. In this way, light reveals not just where matter is, but how the universe itself evolves. What makes these observations even more poignant is that light's lateness becomes its most revealing feature. We often think of delay as loss, as something missing or overdue. Yet for photons, delay is evidence of encounter. Each moment of slowness tells us that gravity has shaped its road, that mass has drawn near, that time itself has changed texture. A photon arriving later than expected is not late. It is delivering a story that could not have been told any other way. Consider one famous example, the lensed quasar known as Refstal, observed by the Hubble Space Telescope. Astronomers watched its multiple images brighten and sequence one after another, separated by predictable intervals. Years later, when the same event reappeared through another part of the lensing cluster, the light arrived exactly when the models had foretold. In that repetition, light replayed across time, we saw confirmation not only of our understanding of gravity, but of light's unerring honesty. It remembers its path so faithfully that even its delay can be foretold. There's a quiet poetry in that precision. Light does not hurry, it obeys the shape of space, and by doing so, it keeps perfect time. The universe, in turn, writes its diary in those differences. When we record the arrival of photons from opposite sides of a lensing galaxy, we are effectively measuring the curvature of existence itself. Each lag is a punctuation mark in the universe's long sentence, a pause that lets the meaning sink in. If you were to translate the equations behind all this into simple language, they would say only this: time and space are woven together, and light traces the threads. Where gravity gathers, the threads twist. Where mass lies hidden, the threads sag. Light does not resist these distortions, it glides through them, recording every dip and detour in its arrival. When we collect that light in our instruments and align its peaks and troughs, the little hums of brightness that flicker across time, we are, in a sense, listening to the echoes of its journey. Each delay is an echo, each echo a clue, each clue another heartbeat in the pulse of the cosmos. And perhaps, beyond the measurements, there is a lesson here for us as well. In a world that prizes immediacy, light reminds us that delay can be beautiful, that sometimes what matters most is not how fast we arrive, but what we gather along the way. The universe has been patient with its own unfolding, allowing light to wander, bend, and arrive in its own time. And because of that patience, we can read its history in the intervals between arrivals, in the pauses that reveal the architecture of space itself. So the next time you look at a photograph of a quasar multiplied into mirrored images, remember that what you're seeing is not just a trick of gravity, but a symphony of timing. Each flicker, each small delay, is a note played by the universe in the key of light, a melody that tells us how long the road has been and how gracefully it was travelled. Sometimes, what light remembers best is simply how long it took to arrive. Light, as fragile as it seems, has a talent for finding its way back to us. Even after a brilliant flare has faded, even after centuries of silence, a soft reflection can return, a memory of brightness carried by dust, These are called light echoes, and they are among the most hauntingly beautiful phenomena in the universe. They prove that sometimes the past is not gone, it is merely scattered, waiting for the right angle to be seen again. When a massive star reaches the end of its life, it dies in an explosion so violent that for a brief moment it can outshine an entire galaxy. The event, a supernova, hurls light in every direction, waves of photons bursting outward like ripples on a pond. Most of that light moves straight through open space, arriving to observers who might be watching from afar. But some of it strikes the cosmic dust floating nearby, tiny grains of carbon and silicate, the ash of older stars, and bounces off just as sunlight scatters through mist after a storm. That reflected light travels a longer route, so it reaches us later. When it does, we see the explosion again, a faint replay of the original brilliance, delayed by years or even centuries. If you could watch this happen from above, it would look like a series of expanding rings of light, rippling through the darkness. Each ring corresponds to dust at a different distance from the source, a cosmic time capsule holding the glow of the past. Astronomers have witnessed these echoes in the aftermath of known supernovae, like SN 1987A in the Large Magellanic Cloud, a small neighbouring galaxy to our own. Decades after the explosion, faint halos of light still appeared around its remnant, each one a reflection of dust clouds lying farther and farther away. Through those echoes, scientists were able to watch the event unfold again, almost as if the universe had saved a recording of its own fireworks. But perhaps the most astonishing example came from much older explosions, ones no one alive had ever seen. In the Milky Way, patches of sky began to reveal strange, faintly glowing arcs. When analysed, their light bore the spectral fingerprint of supernovae that had occurred centuries earlier, long before the invention of telescopes. One of them traced back to Tycho's supernova, first witnessed by the Danish astronomer Tycho Brahe in 1572. The reflected light allowed scientists to study the chemistry of that long-dead star in detail, as though its final flare were still unfolding before their eyes. It was like discovering a centuries-old photograph that still shimmered with motion. Light echoes are not only poetic but practical. By examining how the brightness of the echo changes over time, astronomers can reconstruct the geometry of the dust and even the original light curve of the explosion, how quickly it brightened and faded. In the language of physics, the difference in path length between direct and reflected light determines the delay, but we can understand it more gently. The farther the detour, the longer the memory lingers. Every extra parsec of distance adds another verse to the song of time. What's more, these reflections can reveal the structure of dust itself, how it clumps, how it scatters, and how it fills the interstellar medium. The grains act as countless tiny mirrors, each one reflecting a fraction of the light in a slightly different direction. Some scatter blue light more than red, giving the echoes a pale, spectral hue, like the soft glow of moonlight. Others polarize the light, imprinting a faint twist in its vibration that tells us about the shape and alignment of the dust grains. Through those subtle clues, we learn not just about the explosions that made the echoes, but about the quiet, dusty realms that preserve them. There's a comforting symmetry in all this. Stars live, die, and leave behind dust, and that dust becomes both the veil and the memory of their light. The photons that left a dying star long ago may travel for hundreds or thousands of years before encountering a dust cloud dense enough to reflect them. When they finally do, their faint return allows us to glimpse an event that the universe itself seems unwilling to forget. The cosmos, it turns out, keeps its own photo albums. If you could imagine the journey of one of these photons, it might go like this. It bursts out from the heart of the supernova, carrying the fury of that final moment. It rushes outward at light speed, passing through the shells of gas thrown off by the explosion, and then, instead of escaping entirely, it strikes a grain of dust. The dust is smaller than a speck of smoke, yet big enough to turn that photon aside, sending it in a new direction, perhaps toward us. After centuries of wandering, that single photon arrives in our telescope, still holding the colour, the energy and the pattern of its birth. We, on our small planet, catch it, study it, and realise that it began its journey when empires rose and fell, when the night sky above Earth looked different, when we ourselves were still part of light's future. This idea that the universe can replay its own events through scattered light changes how we think about time. It means that nothing luminous ever truly disappears. It only becomes fainter, folded into the fabric of the cosmos, waiting to be revealed again. In some sense, the sky is full of mirrors, each angled in its own way, reflecting moments from ages past. If we could see all those reflections at once, perhaps we'd witness a shimmering tapestry of every star's life and death, every flare and pulse, all still glowing faintly in the cosmic dust. The science behind these echoes involves scattering angles, distances and travel times, but those are just the mathematics of patience. A beam of light that takes a detour is like a message written long ago, arriving late but still intact. The equations that predict its return are really equations of memory. They remind us that delay does not mean disappearance. In our everyday world too, light echoes exist. When thunder follows lightning, you're hearing the same story told twice, once in light, once in sound, each taking a different path through the air. The lightning's flash is instant, the thunder lags behind, and together they reveal the distance of the storm. The universe does something similar with its own storms, replaying the light to remind us how far away they were, how long they've been gone, and how deeply connected time and distance truly are. There's an intimacy in knowing that the glow from a supernova can reach us more than once. The first time it blazes with immediacy, raw and unstoppable. The second time it returns as a whisper, softened by dust, carrying the warmth of memory rather than the heat of birth. In that soft return we can sense the rhythm of the cosmos, a rhythm built not only on expansion and energy, but on reflection, pause, and remembrance. So when you look up at the stars, remember that the darkness between them is not empty. It holds echoes, faint, patient reflections of what once was, reminders that even light, in its tireless motion, sometimes looks back. The universe does not forget its moments of brilliance. It keeps them safe, hidden in dust, waiting to let them shine again when the angle is just right. Every photon carries a rhythm, a vibration that moves sideways as it speeds forward, like a note rippling through air. This rhythm, known to scientists as polarization, describes the direction in which light's electric field trembles. Most of the time, these directions are random, tumbling freely like leaves in the wind. But sometimes, under certain cosmic influences, those vibrations align or twist, as though light were responding to an unseen melody playing across the universe. Imagine holding a ribbon of light between your fingers. As it travels, the ribbon quivers, up and down, side to side. Now imagine that slowly and gracefully, the ribbon begins to rotate. Its fluttering edge spirals forward, tracing a helix through space. That gentle twist is what physicists call birefringence, a subtle phenomenon where the plane of light's vibration changes as it travels. Here, though, we'll think of it more poetically, as light being guided by a faint invisible wind that no one can feel but the light itself. For centuries, polarization was something we mostly encountered close to home. Sunlight scattering through Earth's atmosphere becomes slightly polarized, giving the sky its deepening shades of blue. Reflections from water or glass can align light's vibration in one direction, which is why polarized sunglasses can soften glare. But on the cosmic stage, polarization becomes something far more profound. Across billions of light years, as photons from the cosmic microwave background traverse the universe, their vibrations can slowly rotate. it's as if the fabric of reality itself is turning beneath them, twisting the direction of their dance by a tiny, immeasurable degree. This rotation, this cosmic birefringence, might be among the faintest signatures of new physics. According to our best understanding, light should travel through empty space without changing its polarization, unless it meets magnetic fields or matter. Yet observations from satellites like Planck and from other sensitive instruments have hinted that there could be a small, consistent rotation, the same everywhere, like a whisper running through the cosmos. If confirmed, this twist could be a sign of something extraordinary. Perhaps space is not entirely neutral. Perhaps there are hidden fields, subtle companions to dark energy, threading through the universe, fields that gently nudge the polarization of light as it moves. In ordinary physics, the electric and magnetic sides of light's wave dance in perfect harmony, perpendicular and balanced. But if there exists a cosmic field that favors one direction over another, it could cause that symmetry to tilt ever so slightly. Light would feel the bias of reality itself, an invisible preference, a cosmic slant that hints at deeper laws still waiting to be discovered. You could think of it this way. Imagine a flock of birds flying through a vast unseen breeze. Each bird represents a photon, its wings beating as it moves forward. If the air is still, the birds all fly straight. But if there's a faint crosswind, each bird adjusts, turning just a little. Over long distances, those tiny adjustments add up, until the entire flock has rotated its direction by a noticeable amount. The birefringence of light is just such a turning, not in space, but in the orientation of vibration, a change invisible to the eye but etched into the light's memory. When scientists study this phenomenon, they describe it with angles and parameters, as if drawing lines on a compass. But behind those symbols lies a simple truth. Light is sensitive to the universe's secrets. It reacts to even the faintest asymmetry, to the smallest imbalance between left and right, matter and antimatter, positive and negative. A single degree of twist over billions of years could reveal that the cosmos itself is not perfectly symmetric, that it carries a memory of its own birth imprinted in polarization. This twisting isn't just theoretical. In the laboratory, when light passes through certain crystals, it experiences the same effect. One orientation of vibration moves faster than the other, causing the beam to rotate. The same principle seems to play out on a cosmic scale. The universe, vast beyond imagination, might be acting as its own slow-turning crystal, gently altering the rhythm of ancient light as it drifts through invisible fields. For the cosmic microwave background, the oldest light we met earlier, polarization is more than a property, it's a language. The slight alignment of its waves encodes information about how matter and energy were distributed in the first moments after the Big Bang. The pattern of polarization tells us whether those early ripples were caused by sound waves, by gravity, or by something stranger still. A small, consistent rotation in that pattern could mean that photons have been conversing with fields that existed since the dawn of time, perhaps even remnants of forces that shaped inflation, the universe's first heartbeat of expansion. Yet there's a beauty in how subtle it all is. The rotation angles are minuscule, smaller than a whisper in the wind, smaller than the tilt of a single snowflake as it falls. To detect them, scientists must measure polarization across the entire sky, comparing directions with unimaginable precision. It's a task that requires patience bordering on reverence. But if we could visualize it, we might see the cosmic microwave background not as a static map, but as a soft spiral of colours, each hue gently rotated by invisible fingers. And behind this science lies a deeper reflection. Light remembers not only where it has been, but how it has turned along the way. Its polarization is a record of the invisible influences it has encountered. Gravity bends its path, heat changes its colour, and now we find that something even more delicate, perhaps a field beyond our current understanding, may twist its very essence. Light, then, is not only a traveller or a witness, but a dancer, spinning slowly to the music of the universe. Some philosophers of physics have suggested that such a symmetry, this faint twist, might even explain why our universe has more matter than antimatter, why something exists instead of nothing. It's only speculation for now, but it's a poetic one, that the slight imperfection in light's journey gave rise to everything we know. From that imperfection came galaxies, stars, and perhaps the possibility of observers who can wonder about it. When we measure the polarization of ancient light, we're doing more than calibrating instruments. We're watching the universe tilt its head slightly, listening for the rhythm of its unspoken thoughts. Every twist, every subtle rotation is like a murmur in a language we're only beginning to translate. And if the cosmos is indeed whispering through these vibrations, perhaps what it's saying is simple. Symmetry is beautiful, but imperfection creates story. A universe where light never twisted would be pure, silent, and forgetful. But ours is one where photons dance and turn, carrying in their spin the memory of all they've touched. Dust, gravity, heat, and fields beyond imagining. Perhaps when we gaze at the night sky, we're not just seeing light that has travelled through time. We're seeing light that has learned to move with the subtle grace of the universe itself. Twisted, yes, but only in the way all stories twist as they are told and retold across the ages. There is a mystery at the heart of light that even Einstein found unsettling, a phenomenon so intimate that it defies the usual sense of distance. It is called entanglement. In the simplest terms, it means that two particles, once connected, can remain linked no matter how far apart they travel. Change something about one, and the other responds instantly, as though distance were only an illusion, as though the universe itself were whispering between them. Now, imagine two photons born together, perhaps in the same spark of an atom's energy transition, or in the dying flare of a star's decay. In that instant of creation, their properties, their rhythm, polarization, or spin, become matched, like two dancers beginning the same choreography. Once released, they travel away from each other at the speed of the light, carried by the expanding fabric of space. One might head toward the edge of a nebula, the other toward some future planet not yet formed. And yet, no matter how far they drift, something between them remains connected. If you could measure the direction of one photon's vibration, the others would always answer in harmony, even if the two were separated by billions of light years. There is no known signal that passes between them. It happens too quickly for any message to cross the distance. This strange instant of correspondence is what Einstein called spooky action at a distance. But what we now understand is that no action travels between them at all. Their connection is not through space, it is outside of it. Entanglement doesn't send messages, it reveals that, at some level, there may never have been two separate things to begin with. You could picture it like this. Imagine lighting two candles from the same flame. Blow one out, and you might feel just for a moment that the other flickers, not because the air moved, but because they were once part of the same fire. That's the feeling of entanglement, a memory of shared origin that distance cannot erase. For decades, the idea sounded too magical to be real. Scientists debated whether there were hidden mechanisms that could explain it, small variables secretly influencing both particles to behave in the same way. But careful experiments, repeated again and again, have shown that the effect is real, and that no hidden signal could account for it. It's as if the universe insists that wholeness comes first and separation second. The mathematics that describe this phenomenon are full of symbols that look intimidating. Probabilities, amplitudes, complex phases that dance like shadows on a wall. But we can hear their meaning more softly. They tell us that what we see as two particles are actually part of one shared wave. a single pattern expressed in two places. Like ripples on opposite sides of a pond, they're connected through the water beneath, moving in harmony even when the surface seems still. In laboratories on Earth, scientists have used entanglement to link photons over increasing distances, from one side of a city to another, and eventually between ground stations and satellites orbiting above the planet. Each time they measure one photon's orientation, the other responds exactly as predicted. It's as though the light remembers its twin, even when the two have long since lost sight of each other. And if such connections hold true across a few kilometers or a few thousand, could they also exist across the cosmos? When photons were born in the early universe, some pairs might have been entangled and then separated by the expansion of space itself. Billions of years later, they could now reside on opposite sides of the observable universe, yet still carry that hidden bond. The night sky above us could be full of such silent partnerships, pairs of photons whose shared story is still unfolding, written not in position or time, but in the unseen symmetry of their vibrations. If this sounds mystical, it isn't meant to. Entanglement is one of the most rigorously tested ideas in quantum mechanics, but it does hint at something deeper, that information, the pure essence of pattern and relationship, might be the fundamental currency of reality. Space and time may be the stage, but information is the script that never tears. Some physicists describe entanglement as the glue that holds space-time together. It's a poetic notion that the fabric of the cosmos might be woven not from threads of matter, but from threads of correlation, patterns that remain synchronized across distance. In that sense, every photon is not an isolated traveller, but a participant in a grand, interconnected performance. Each beam of light contributes to the coherence of the whole, like instruments in a vast orchestra, playing a song too complex for any one listener to hear in full. In practical terms, entanglement has become a tool for new technology. Quantum communication systems use it to send information securely, ensuring that any attempt to intercept the signal instantly changes its state, revealing intrusion. Quantum computers rely on entanglement to process many possibilities at once, performing calculations that ordinary machines could never finish. These are modern miracles of engineering, but they all trace back to the same gentle truth. Connection is written into the heart of light. If you could stand outside of time and watch two entangled photons part ways, you might see their waves stretching through space like twin threads of silk, woven through the same cosmic fabric. No matter how far apart they drift, they still belong to the same pattern. Measure one, and you tug gently on the thread that binds them both. Their unity is not a matter of distance, but of definition. A reminder that separation, though real to us, might be an illusion born of perspective. Some have wondered whether this interconnectedness could extend beyond particles, to systems, to consciousness, to the cosmos itself. Science doesn't yet know, but the idea is tender to imagine, that maybe the reason the universe feels whole is because at some level it truly is. Perhaps photons are not just witnesses of the past, but participants in an unbroken web of relationships that transcend space and time. It's humbling to think that when you look at a star, some of the photons entering your eyes might once have been born entangled with others that are now far beyond your reach. In absorbing them, you become part of that continuity, one more link in light's long chain of memory. Entanglement tells us that even in the emptiest reaches of space, nothing exists entirely alone. There are no solitary travellers, only companions moving in quiet synchronization. It's a truth both scientific and poetic, that the universe, in all its vastness, might still behave like one indivisible whole. And so, as we continue our journey through light's memory, we carry this understanding with us. That connection is not the exception, but the rule. The photons that cross the darkness are not strangers passing by. They are fragments of a single, luminous story, threads that stretch across eternity, woven from the same pulse of creation. If light has a soul, then perhaps it dreams of rest, a moment when it can stop moving, just for a heartbeat, and remember itself. For most of its existence, light is pure motion, always travelling, always free. It cannot be still. A photon that stops moving would simply cease to exist, because motion is its essence. Yet scientists have found ways to slow it, to let it pause inside matter without losing its identity, as if they've built a place where light can take a gentle breath. This idea may sound like fantasy, but it's one of the quiet marvels of modern physics. In laboratories filled with lasers and clouds of ultra-cold atoms, researchers have learned to coax photons into halting, not by trapping them in mirrors or boxes, but by weaving them into the fabric of matter itself. They call it quantum memory for light, though you might think of it more simply as catching a sunbeam and asking it to wait. The process begins with a strange kind of stillness. Inside a vacuum chamber, scientists cool a collection of atoms, often rubidium or cesium, to near absolute zero, where they hardly move at all. In this calm, the atoms behave like a single synchronized organism, a delicate mist ready to receive light. Then, a faint pulse of laser light, perhaps just a few photons strong, is sent into the cloud. At the same time, another carefully tuned beam, called a control field, interacts with the atoms. Together, the two beams create what is known as electromagnetically induced transparency, a phrase that sounds mechanical but means something quite poetic. The light teaches the atoms how to let it through without destroying it. As the pulse enters, it slows down dramatically, from 300,000 kilometers per second to a crawl, perhaps just a few meters per second, even less. Inside the cloud, the information that makes up the light, its phase, its color, its rhythm, transfers into the atoms themselves, becoming a collective vibration of their internal states. For a moment the light is gone. The atoms are holding its pattern, storing its memory. Then, when the control field is turned back on, the stored vibration releases, and the original light pulse emerges once more, unchanged. It's tempting to think of this in mathematical terms: energy levels, frequencies, coupling constants. But beneath the notation lies a gentle truth. What these experiments show is that light can pause within matter without losing its story. The atoms act like librarians, keeping a record of what the light was, its timing, its tone, its message. When released, the light continues its journey as if it had never stopped. There is a quiet beauty in the image of light resting inside atoms, like a bird folding its wings within a tree before taking flight again. It suggests that motion and stillness are not opposites, but parts of the same dance. The photon doesn't truly stop. Its energy simply takes another form, distributed among the atoms that cradle it. For that brief moment, matter and light share a single identity. In recent years, scientists have managed to extend the length of this pause, from microseconds to milliseconds, even seconds in some systems. It may not sound like much, but for a photon that normally crosses the room in a fraction of a billionth of a second, it is an eternity. These experiments have laid the groundwork for a new kind of technology, quantum communication networks, where information can be carried by light and stored temporarily in matter before moving on again. They're building, piece by piece, an architecture that mirrors the cosmos itself, light as messenger, matter as memory. But beyond the engineering lies something more philosophical. If light can be stored and released without losing its essence, then memory itself may not be limited to the realm of life. It may be an inherent property of the universe, a capacity to hold patterns and release them later. Atoms, photons, even space-time itself seem to possess this rhythm of remembering and forgetting, like a cosmic heartbeat that keeps track of its own pulses. You might imagine that when light rests inside matter, time also softens around it. The equations of physics describe how the information of the photon is preserved in quantum superposition, a delicate state where possibilities coexist, waiting for a signal to awaken them. Translated gently, this means that the light is not gone. It is dreaming. Its presence lingers as potential, suspended between being and becoming. The word quantum can sound intimidating, but at its core it simply means that nature writes its stories in discrete steps, tiny packets of energy and information. Quantum memory, then, is the act of preserving one of those packets, a single syllable of the universe's speech, and allowing it to be spoken again later. It's as though reality itself can rehearse its lines, perfecting the delivery of meaning across time. There's a parallel here with human experience. Our own memories are fragile pulses stored in the matter of the brain, chemical patterns that encode light, sound, emotion. When we recall a moment, we reconstitute it from those patterns, letting it shine again for a brief instant before it fades. The quantum memory of a light operates in a similar way, though stripped of emotion and story. Pure physics, pure preservation. It's a reminder that remembering is not unique to consciousness. It may be a universal gesture of energy as it changes form. Some researchers have even speculated about using these principles to build a quantum internet, where photons carry entangled information across vast distances and deposit it safely in memory nodes until it is needed again. The practical goal is communication that is unbreakably secure. Messages that cannot be copied or intercepted because the very act of reading them would alter their state. But behind that ambition is a deeper fascination, the idea that we could someday build networks that mirror the universe's own way of keeping in touch with itself. From a more poetic view, these experiments suggest that light, in learning to pause, also learns to trust, to surrender its motion and allow itself to be held. In doing so, it shows us a different kind of strength, not persistence, but patience. The same patience that lets photons travel across billions of years without aging allows them too to rest inside a whisper of matter for just long enough to be remembered. And perhaps that's the essence of memory in all its forms. Whether stored in atoms, in neurons, or in the folds of space-time, memory is what turns motion into meaning. It's the way the universe pauses to acknowledge its own story before continuing. When scientists speak of trapping light, what they've really done is teach the universe how to linger, how to hold its breath between beats. So, the next time you see sunlight glancing off a window, or a pulse of laser light tracing a pattern on the wall, imagine that somewhere, in the quiet depths of a laboratory, another beam is resting, still bright but folded within a cloud of atoms, waiting to be released. It's a reminder that even the swiftest traveller in the cosmos has moments of stillness, and in those moments, light proves what it has always known, that to move endlessly forward, one must first learn how to pause, how to remember, and how to begin again. If you listen closely enough to light, you'll find that it's never silent. It speaks in rhythm and interference, in peaks and valleys of brightness, in soft modulations that overlap and create patterns richer than any single beam alone. Every photon is part of a dialogue, not just between stars and space, but between every place and every moment that light has ever touched. This conversation is invisible to our eyes, but it fills the universe like music beneath a long quiet. To understand it, imagine two beams of light meeting. They cross paths, and for an instant they blend. Where their crests align, the light brightens. Where a crest meets a trough, they cancel, leaving a faint shadow. This simple interaction, called interference, is one of the oldest discoveries in optics, yet it reveals something profound. That light is not only a traveller but a communicator. It doesn't just move, it exchanges information about its journey through the subtle patterns it leaves behind. When Thomas Young first showed the interference of light in the early 19th century, he proved that it behaves as a wave, not a stream of particles as once imagined. Two narrow slits, a screen, and a beam of sunlight created stripes of brightness and darkness, like ripples overlapping in a pond. But what that experiment really showed, in deeper terms, is that every photon carries with it the potential for conversation. When one beam meets another, they don't collide like marbles. They share space, blending their histories into something new. This same principle is what makes holograms possible. A hologram is nothing more than a frozen interference pattern, the imprint of how light from an object interacts with light from a reference beam. When illuminated again, the hologram recreates the full three-dimensional image of the original scene, complete with depth and perspective. You can walk around it and see the object from different angles, as though it was still there. The light doesn't reproduce the object itself, only the information about it, a perfect illusion of memory suspended in thin air. Some scientists have suggested that the universe might work in a similar way, that reality itself could be a hologram. The idea doesn't mean that we live in a simulation, or that matter is unreal, but rather that everything we experience, space, time, gravity, may emerge from the underlying information encoded at a deeper level. In this picture, the surface of reality contains the data, and the three-dimensional world we see is a kind of projected conversation among photons, particles, and fields. It sounds abstract, yet the idea finds echoes in how light behaves. Every photon carries phase, the timing of its wave, and that phase encodes how it has interfered with everything else it has met. The pattern of those phases across space is like the handwriting of the universe, recording where light has been, what it has touched, and how it has changed. Even when two photons never meet again, their interference patterns stored in the field around them preserve the memory of their brief encounter. You could imagine the entire cosmos as a grand conversation in photons. The light from a star carries whispers of its temperature, its motion, its chemistry. When that light meets dust, it scatters and changes tone, adding a new voice. When it bends around gravity, it stretches and deepens like a note falling in pitch. When it interacts with other radiation, it forms chords, harmonies of colour and phase that fill the electromagnetic spectrum. And when all of these waves overlap, they compose the intricate texture of the night sky, a living, breathing record of all the conversations light has ever had with matter. If this sounds musical, that's because it is. Scientists describe interference through something called a superposition of waves, but the word simply means that many melodies are playing at once, weaving into each other. In mathematics, these patterns can be represented as amplitudes and phases, but in our softer language, they are harmonies and timing, the rhythm of reality unfolding. In the quantum world, the conversation becomes even subtler. A single photon can interfere with itself, taking two paths at once, and recombining as though it had been in two places simultaneously. This isn't a trick of measurement, it's the natural language of probability written in waves. The equations that describe it, with their complex numbers and oscillating phases, are just ways of capturing that whisper. I have been here and there, and both at once. If you could translate those formulas into sound, they would resemble overlapping tones that rise and fall in infinite variation, always coherent, never chaotic. In recent decades, physicists have used this whispering property of light to build instruments of astonishing sensitivity. Interferometers, devices that split and reunite beams of light, can detect movements smaller than the width of an atom. One such instrument, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, uses interference to measure ripples in space-time itself. When two black holes collide, they send out waves that stretch and squeeze the fabric of the universe by less than a fraction of a proton's diameter. Yet through interference, light can hear it. The changing pattern of bright and dark fringes in the laser beams reveals the faint tremor of space, turning an almost imperceptible distortion into a message. The sensitivity of these measurements reminds us that the universe is not silent but symphonic. Light hears the subtlest tremors, records the faintest motions and carries them forward. In that sense, every photon is both a note and a listener, a messenger that not only travels but also perceives, translating movement into pattern. If reality is indeed holographic, or at least deeply interconnected through these overlapping waves, then every photon we see is part of a vast network of memory. No event ever happens in isolation. It's woven into the field of all other events, its vibrations rippling outward indefinitely. The past continues to speak through these patterns, encoded in the phase of light that reaches us. Perhaps this is what ancient starlight truly is. Not just illumination, but communication. Each beam that reaches our eyes has interfered with countless others, each carrying traces of the cosmic dialogue that preceded it. By studying the faint variations in that light, we learn not only what the universe is made of, but how it converses with itself, how energy, matter, and time exchange information in the quiet pulse of existence. And maybe, on some deep level, we're part of that dialogue too. Our eyes, our minds, and the tools we build all depend on light's ability to carry information. Every photograph we take, every reflection in a window, every pattern of brightness and shadow is a small continuation of the same universal process. Light recording, translating, and retelling the story of where it's been. The universe, it seems, is fluent in this invisible language, and though we can't hear the conversation directly, we can see its traces everywhere, in the ripples of interference, in the shimmering of a soap bubble, in the faint lines of a hologram. Light doesn't just show us the world, it tells us how the world connects. Every flicker is a word, every reflection a phrase, every interference pattern a sentence in the grand dialogue of creation. Perhaps that's what makes starlight so comforting. When you stand beneath it, you're listening, not to silence, but to the universe speaking softly in light. The conversation never ends. It only changes form. And as you look up, you become part of it, another listener in the choir of photons that remember everything the cosmos has ever said. When you look up at the night sky, you're not simply seeing light, you're seeing time. Every star above you, every galaxy faintly glimmering at the edge of sight, is a moment already gone, still travelling toward you in waves of colour and warmth. The farther away you look, the older the light becomes. The sky, then, is not a picture of what is, but a mosaic of what was, a layered memory of the universe remembering itself through light. It's easy to forget this. We think of seeing as something immediate, a direct experience of the present. But even the light bouncing from the moon takes more than a second to reach your eyes. The glow from the sun carries an 8-minute delay, the time it takes for photons, born in its fiery heart, to cross the gulf of space to Earth. The light from distant stars has travelled for years, centuries, or millennia before reaching you. And the faint glow from the most ancient galaxies has been on its way since the dawn of time itself, stretched and softened by the expansion of space. That delay, that patient travel is not just a limitation, it's the very reason we can read the universe's history. Light gives us the privilege of time travel. Every telescope is a time machine, every photograph of the cosmos, a layered archive of moments unfolding in reverse order. To gaze outward is to look backward. Each photon you catch is an emissary from a different chapter of cosmic memory. Even our simplest technologies are built upon this gift of remembrance. A camera doesn't capture the present, it gathers light that has already left. A mirror doesn't show you now, it reflects a moment that left your face a few billionths of a second earlier. Though the difference is small, it reminds us that seeing is always an act of receiving, a collaboration between the past and the present. On a cosmic scale, the same principle becomes astonishing. When the Hubble or James Webb Space Telescope stares into the deep sky, it collects light that began its journey billions of years ago, when the first galaxies were forming. The image that appears, the delicate swirls of colour and dust, is a photograph not of existence as it is today, but of the universe as it once was, long before Earth took shape. Through light, the cosmos reveals its own autobiography. Scientists translate this glow into knowledge. They analyse the colour of the light, how much it has shifted toward red, to measure how far it has travelled and how quickly the universe has expanded since its release. This shift, which could easily be expressed in symbols, is better imagined as the deepening tone of a song as it slows. Space stretches, and light's rhythm slows with it, changing the melody of time. In this way, the cosmos remembers its own growth, recording it in the softened music of the galaxies. Even the light you see during the day, sunlight scattered through air, reflected from leaves and windows, is part of that continuum. Each photon striking your skin was forged in the sun's core before any human history existed. It spent thousands of centuries bouncing around inside the star before escaping into open space, then just 8 minutes rushing toward Earth to land softly on your hand, on your face, on your world. The warmth you feel is not only energy, it is a message sent long ago, finally arriving. The same applies to the light we create ourselves. Every lamp, every candle, every glowing screen contributes to a network of radiance that joins the universe's great archive of light. Once released, those photons continue outward, fading but never truly vanishing. Somewhere, billions of years from now, the faintest traces of Earth's light, our cities, our fires, our signals, will still be travelling, rippling through the dark as evidence that we were here. In this sense, light turns everything into memory. The universe doesn't keep diaries written in ink, it keeps them in radiation. Every event that releases energy, a supernova, a sunrise, a lightning strike, a heartbeat, leaves its trace in photons. They carry those imprints forward indefinitely until they're absorbed, scattered, or bent into new paths. And even then, their influence continues, folded into the next generation of light. The cosmos is self-recording, always writing, never erasing. Perhaps this is why light feels so spiritual to us. It connects us with the past in a way nothing else can. The glow of a candle may seem fleeting, but some of its photons will escape into space and wander forever. Somewhere in the far future, a traveller might detect them and know that here, in this small moment, warmth existed. The philosopher in you might wonder, if every photon is a memory, then what happens when we look back? Are we, by observing, also participating in that memory? The answer is quietly yes. When your eyes absorb starlight, you become part of its record. The light that began its journey billions of years ago ends within you, in the chemical reactions of your retina, in the tiny pulses of your neurons. You are the completion of that story. The cosmos remembers itself through you. There's something humbling in that realization. You're not merely observing the universe, you're helping it see. The atoms in your eyes were once inside stars. The photons they absorb were born from other stars, and together they form a circle of remembrance. Light observing light, existence recognizing itself. In scientific terms, we might say that the act of observation collapses probability into reality, but said more gently, we could call it awareness. The universe awakening to its own reflection. You're both the witness and the continuation of that reflection. When you look at starlight, you're also looking at the echo of your own origins. Every photograph, every mirror, every shimmering horizon is a reminder that nothing in the cosmos ever truly fades. The light that leaves will travel until something receives it. A particle, a world, a mind. In that exchange, the memory of the universe is refreshed. Light keeps the story alive by moving, and we keep it alive by noticing. So the next time you find yourself beneath a quiet sky, try to imagine what you're really seeing. Each star is a word, each galaxy a sentence, each faint smear of light a chapter written long ago. And you, standing there, are the reader. the interpreter of the story that light has been telling since time began. You are part of the remembering, part of the endless reflection that gives the universe its meaning. Light does not age as we do. It doesn't decay or forget. It carries the imprint of everything it has touched, unchanged in its devotion to the journey. And in that way, the universe, through light, never loses its memory. It only learns to see itself more clearly with every passing photon, through stars, through dust, through you. There comes a moment, near the end of every long night, when the first hint of dawn brushes the edge of the world, the sky lightens almost imperceptibly, and the dark begins to soften. It's easy to overlook, but that slow transition from black to blue, from silence to sound, is one of the oldest rituals in the universe. It's not just the earth turning toward the sun, it's light returning to remind us that time still glows. For all the grandeur of cosmic discoveries, the bending of galaxies, the quantum entanglements, the twists in polarization, what light truly reveals is not something distant, but something deeply personal. We are built to receive it. The rods and cones in our eyes, the pigments in leaves, the chemical reactions in every living cell, all attuned to light's frequencies. Every sunrise that warms your skin, every reflection that catches your eye, every photograph that holds a moment still, all of them are acts of connection between your body and the wider cosmos. In the language of physics, light is an electromagnetic wave, a vibration of energy that travels through space at a constant speed, 300,000 kilometers every second. But translated into something gentler, we could say that light is the pulse of the universe, the tempo that keeps everything in rhythm. It synchronizes life to the turning of the planet, marks the passing of days and seasons, and ties us, without our noticing, to the heartbeat of stars. Every photon that reaches you carries not only information about where it came from, but a quiet invitation to notice. To see is to participate in the universe's remembering. When your eyes capture the light reflected off a loved one's face, that light, born in the heart of the sun, has travelled millions of kilometres, bounced from atmosphere to skin, and found its way to you. The warmth you feel is a journey completed, a circuit closed between star and soul. In a sense, light and life are two versions of the same story, energy learning to remember itself. The chemical reactions that power your body are just organised forms of that same process. The food you eat is sunlight transformed by plants into sugars and fibres, locked away until you release it again. When you breathe, when you move, when you think, you're burning the memory of light. The fire in your cells is the echo of photons captured long ago, and perhaps that's why we find light so emotionally powerful. It's not merely a visual experience, but a recognition, a reunion between what we are and what we came from. When sunlight falls on your skin, you're being touched by your own history. When you light a candle in the dark, you're recreating the first act of creation, turning energy into meaning. Time, too, flows within that same pattern. Light gives us a way to measure its passing, but it also reveals that the separation between past, present, and future might not be as strict as we imagine. A photon leaving a distant galaxy billions of years ago is still part of that event, even as it arrives here and now. Its journey folds time together, connecting moments that, from our perspective, seem impossibly far apart. The light you see tonight from a star is the star's memory of itself still unfolding in the present. Einstein once wrote that for light, time does not pass at all, because it moves at the cosmic speed limit. From its own perspective, the photon's birth and its arrival are one and the same moment. That's hard for us to imagine, but it carries a soft wisdom. To light, there is only now. Every photon that touches you is experiencing its entire existence in an instant, born, travelling, arriving, all at once. When you catch it, you're sharing that eternal now, In a way, this teaches us something about being alive. We too move through time, stretching between memory and anticipation, but every so often, there are moments that feel timeless. The hush before dawn, the warmth of someone's hand, the pause before sleep. In those moments, our perception of time softens. We stop rushing forward and simply exist. It's not so different from light's eternal present, a glimpse of how the universe feels from the inside. Light also binds us across generations. The photons reflected from your face now may one day strike the retina of someone who has not yet been born. In a photograph, a video, a memory preserved in digital light. Just as we look at ancient starlight and learn about galaxies that no longer exist, future beings may look at our captured light and learn who we were. In that sense, every image, every reflection, every spark of light we release becomes part of the universe's archive. And there's another layer still. The same light that reveals the external world also illuminates the inner one. The patterns of electric impulses inside the brain, the shimmer of thought itself, are waves of energy not unlike those that travel through space. Consciousness too is a kind of radiance, a way the universe becomes aware of its own unfolding. When you have a sudden insight or remember something long forgotten, it feels as though a small light has turned on within you. That feeling is not a metaphor, it's literal. The movement of electrical charges and chemical signals glowing quietly inside your mind. Perhaps that is the most intimate connection of all, the realization that the same principles governing the stars also shape our awareness. The photons that move through space, bending, scattering and carrying memory, are echoed in the thoughts that move through us. Each moment of understanding, each spark of curiosity is the mind's own version of light, a brief but brilliant act of seeing. The story we've followed, from the birth of photons in stars to their echoes in dust, their entanglement across space, their memory stored in matter, all leads here to this small but immense fact. Light connects everything. It threads through galaxies and through hearts, through equations and emotions alike. It carries the record of the universe and the reflections of our lives, binding them into a single, luminous continuity. And maybe that's what the universe has been doing all along, not merely expanding, but remembering. Each photon is a page in that cosmic diary, and every one of us is part of its reading. To live is to absorb light, to release it again, to pass the memory forward. So when the morning comes and sunlight touches your face, think of the journey it has made, from the heart of a star, across millions of kilometers, through air and cloud, to this single instant of warmth. Think of how it carries not just energy, but story. The story of time, of connection, of life itself. And know that in that moment, the universe is not somewhere far away. It is here, remembering itself through you, through your eyes, your breath, your thoughts, your quiet wonder. Because in the end, light doesn't just reveal the world, it reveals that you are part of it, a reflection in its glow, a brief but beautiful note in the eternal song of time. And so, as you rest, may you feel that connection to the stars, to the warmth around you, to the gentle pulse that moves through all things. The light that began at the dawn of creation still travels through you tonight. Sleep peacefully in its memory, and when you wake, let it remind you that time still glows